How do conditional VAE GANs combine the strengths of variational autoencoders, VAEs, and GANs for data generation?
Conditional VAE GANs merge VAEs and GANs to improve data generation quality. They use VAEs for structured latent space learning and conditioning and GANs for high-quality data generation. This combination ensures that the generated data is not only realistic but also structured and controllable, making conditional VAE GANs valuable for tasks that require both structured representations and realistic content generation, such as image synthesis with specific attributes.
What is recurrent GAN training, and how does it enable GANs to generate sequential data with coherent temporal dependencies?
Recurrent GAN training involves using recurrent neural networks, RNNs, or LSTM units in the GAN architecture to generate sequential data with coherent temporal dependencies. These recurrent components capture sequential patterns and help maintain continuity in the generated data. Recurrent GAN training is applied in tasks like video generation, dialogue generation, and music composition, where generating sequential data with temporal coherence is essential.
How can federated learning GANs be employed for collaborative data generation across decentralized devices while preserving data privacy?
Federated learning GANs extend GAN training to decentralized environments where data is distributed across multiple devices or locations. They allow GANs to be trained collaboratively while preserving data privacy. Federated learning GANs aggregate model updates rather than raw data, ensuring that data remains on user devices and reducing the risk of data leakage. This approach is valuable for privacy-preserving data generation tasks, such as generating personalized recommendations without centralizing user data.
What is reinforcement learning for GANs, and how does it enable GANs to learn better data generation policies?
Reinforcement learning for GANs incorporates reinforcement learning techniques to improve the training and policy learning of GANs. It involves training GANs using reward signals that guide them toward generating desired data distributions or attributes. Reinforcement learning for GANs is valuable for tasks where specifying explicit reward signals can help shape the data generation policy effectively.
How do spatial GANs enable data generation that respects spatial relationships and structures in the generated content?
Spatial GANs focus on generating data that adheres to spatial relationships and structures within the content. They incorporate spatial constraints, convolutional layers, or structured latent spaces to ensure that the generated data maintains spatial coherence. Spatial GANs are valuable for tasks like image synthesis, scene generation, and content composition that require preserving spatial attributes and structures.